I come to AI Ukraine every year, and I'd like to begin with a huge thanks to all of the organizers who make this conference great each and every year is better than the last. So welcome, thank you for being here, thank you for listening to me. And this year, I wanted to make it a more technical talk, and I tried to write an abstract that would discourage people from attending. I see that I failed. So before I begin, how many of you actually have heard about synthetic data for deep learning? Okay, a lot of people, good. How many of you know what domain adaptation is in general, just what the term means? Less of you, okay. How many of you know how a GAN works, a generative adversarial model? Okay, okay. Those of you in the back, it might be hard to see. The screen is very large, as I expected, but you are kind of far away. But anyway, I will begin with a very small, very brief introduction into synthetic data, and I apologize to those of you who already know. I will explain what it is and why it is important for deep learning these days. And then we'll dive right into the GANs, okay? So this is a typical life cycle of a deep learning model, right? First, you need to collect the data, then you need to annotate the data, then you train your model, and that's where the magic happens, and that's where, and that's what most of the talks here are devoted to. And then you deploy, and that's what a smaller part of the talks here are devoted to, and then you need to maybe compress your model and make it work on a mobile device or something like that. But today, we will mostly talk about something that makes the first two steps easier and that makes the third and fourth step possible and hopefully better working than without it. So maybe another question for the audience. How many of you have ever engaged in data labeling? Okay, how many of you have tried to label data for computer vision? Something like object detection or segmentation. Much less people. And there is a reason for that. Data labeling is hard, and data labeling is extremely boring, okay? And especially even for standard computer vision problems like object detection or segmentation, usually it's less of a problem to collect the data, to gather the images, right? If you want to recognize cows, you go on Google and you download 1 million images of cows, no problem. But then, if you want to actually recognize the cows on a field like here, you need to go through your data and manually put the bounding boxes. Do I have a pointer? Yeah. And manually draw the bounding boxes around each and every cow, which is honestly a huge pain in the neck, right? And if we are talking about segmentation, it becomes even harder. And usually, of course, nowadays people don't do it completely by hand. People have some sort of a preliminary model that gives you a rough segmentation result, and then you fix it by hand, and that's your golden standard, that's your ground truth. But still, it's a very laborious process, and it requires a lot of man hours, even if not very highly qualified man hours, right? But so this is very expensive, and if we are talking about recognizing cows, maybe you can find a data set on the internet, right? But if as soon as you start to have any kind of problem where you need to recognize specific objects where you have the data, but not many other people have the data for these specific objects, you need to do the labeling yourself, right? And that's hard. So data is actually the limiting factor, and data labeling is usually more of a limiting factor than data collection, although it depends on the domain. So synthetic data is one way to get around this problem, right? Usually, when people speak of synthetic data, and here today I will be talking exclusively about computer vision and synthetic data for computer vision, it means that you have some sort of an external process, like a 3D modeling, where you create the 3D model of stuff that you want to recognize. And then, so this is still manual labor, right? But then, after this upfront investment of manual labor, you can actually generate a lot of, you can generate as many images as you want. You can generate images in all sorts of conditions and also from all sorts of angles in different modalities. You can have any sort of labeling for these images. And you can have, of course, object detection. You can have segmentation. It's pixel perfect because you know for every pixel on your image, you know what object it belongs to. And what's even more important, you can have the kind of labeling which is nearly impossible to do by hand, right? So what if you need to do depth estimation? For example, if you're training a self-driving car, then something like depth estimation is a necessary part of it, and estimating the distance to objects. And for that, you simply, I mean, people don't work like this, right? So I can tell you which one of you is closer to me or further from me, but I cannot tell you the distance, right? And you can either have you either have to have special hardware that the radars, lidars, whatever, and collect your data set with very expensive and cumbersome special hardware, or you can go the synthetic route and you can try to generate a synthetic data set where again the depth estimation will come for free because you know the 3D scene that you're rendering. And so on and so forth. So it's easy to add variety. Once you have a model, you can just apply different textures, different skins, and you will have a lot of different objects. And yeah, and in a way, you can think of what you can do with synthetic data as parallel to what is called data augmentation. I suppose everybody who has worked with computer vision ever knows what data augmentation is, right? It's like an inevitable step of working with any serious computer vision problem. On the training stage, you take your input images and you modify them in some way. And usually by data augmentation, people mean some simple modifications like affine transformations, rotations, crops, I don't know, Instagram filters, changing the brightness, something like this, right? Why these transformations are so simple? Because the main requirement for a transformation in data augmentation is that they do not change the labels, or they change the labels in predictable ways, because there is no way for you to get a new label, right, unless you manually relabel it from scratch. So for example, here, if I want to recognize this person, I know that this kind of transformation does not change the identity of the person. And if I want to do segmentation, for example, if I want to cut out the person, I can easily transform the mask from here to here because it's just an affine transformation, right? But with synthetic data, you can do much more complicated transformations, right? You can, for example, rotate the face. And there is no easy way to rotate a face on a 2D image, of course. And we will actually speak about how people do it, and it will not be easy. And so on and so forth. I will not go through this slide. It doesn't really matter for us now, but there are a lot of transformations that you can do with synthetic data that are impossible to do in real data, and there is a lot of variety, right? And this variety multiplies and explodes, and there is an exponential blow up in the number of images that you can obtain with all of these transformations. Okay? Right, I've already talked through this. And there are a lot of applications already. I hope that soon a survey will come out from myself about synthetic data in deep learning now. And I can already say that synthetic data is increasingly being used across all sorts of computer vision problems. So face recognition, definitely autonomous vehicles, and anything related with robotics, because in robotics, be it self-driving cars, unmanned autonomous aircraft, actual robots that manipulate things. In robotics, you usually want to do reinforcement learning or at least some kind of interaction with the environment, right? You want to have your robot do stuff and see how the environment responds. And that is, of course, completely impossible to do unless you have either a real environment or a simulated environment, and the real one is very expensive. Retail applications, gait estimation, animal applications, gesture recognition, medical imaging, all sorts of things. There are some specifics in each of these domains. For example, in medical imaging, usually the problem is not that you have a lot of data, but it's hard to label. In medical imaging, usually you just have very little data, right? But still, you can try to solve it with synthetic. And so far, what I've been saying was basically that synthetic data is great, and synthetic data is the way to go for all computer vision applications, and you can have a synthetic environment where you can train everything that you need, and then it will work straight out of the box. Naturally, life does not work this way, right? So if you have a synthetic environment or a synthetic data set, elements of this environment and images in this data set will not be completely realistic, right? Even if you go to, I don't know, an animated movie where like the whole power of Disney has been put into making this stuff realistic, it's still not, right? You can still tell it's a cartoon. And you can tell, and of course, a deep learning model can. So it is, as soon as you start to use synthetic data, you're faced with the problem called domain transfer. Is it here? Yeah, synthetic to real domain transfer. So you want to take models trained on synthetic data, or maybe on a hybrid data set where you have a little bit of real data and a lot of synthetic data, and then you want to transfer the model into, so that it will work on real data sets, because your ultimate goal is never is never in the synthetic environment. Your ultimate goal is in the real world, right? So the transfer is a hard problem, and it is actually interesting that by now some works are beginning to appear where this problem does not arise. And I want to highlight, for example, Dactyl. This is a robot from OpenAI, which has learned to do this kind of manipulation, like a five-finger manipulation with small objects. It has learned it in a completely synthetic environment. These are the real screenshots from the environment. And then it worked. It did the transfer automatically somehow, without any explicit domain adaptation in the loop. And that is interesting. And maybe with time, we will see more of this. But I still think that for most applications, you will have to do some kind of explicit domain transfer. You will face this problem, and you will have to do something about it, right? And currently, there are two main ways to address this domain transfer problem. One of them, so it's a bit of a superficial distinction, but I like to make this distinction. I think it's useful. One of them I call refinement, and this means changing the data, the synthetic data, to be, I don't want to say more realistic, I want to say more useful for models that are supposed to work on the real world. That's a subtle distinction, but sometimes it comes into play. So refinement is when you actually, in your process, you have, at some point, the synthetic data being changed into something, and then you can look at this more realistic data, and then you train on this more realistic data, and your model supposedly improves. So this is the refinement side of things. And again, I call it domain adaptation. It's a market term. It depends on how you define it. Sometimes refinement is also considered to be part of domain adaptation, but let's speak of domain adaptation at the model level. So at no point here there is no point in the pipeline where you're changing your data. What you're doing is you're changing your model or the training process in such a way that you can train now on synthetic and then transfer to real easier. And we will see both, both sides in the talk. So I want to begin with one specific problem, with a case study. And this is a very famous case study for synthetic data. This was, like, I think, the first famous paper where synthetic to real refinement actually worked. And in a few minutes, I will explain why and why this is so easy a problem for synthetic data. But still, so the problem is gaze estimation. Gaze estimation means it's something very useful for mobile, and it's something very useful for, well, okay, I wanted to say eye tracking, but it is eye tracking, right? So gaze estimation is given the image of a person, a close-up of a face, determine where the person is looking at. And by where, you usually mean like the angle where the gaze is directed, right? So this is the target variable. And this slide shows some state-of-the-art architecture for gaze estimation from 2015, when there was no synthetic data in this field. I won't go into the details here, it doesn't really matter for us, but still, okay, so there was some kind of state-of-the-art, and it was, of course, a convolutional network with some complications. Then, in 2016, there was a big effort for creating synthetic data for gaze estimation. So a bunch of people got together and tried to make as realistic, cartoonish eyes as possible. And they succeeded pretty much. They made a special modeling system called Unity Eyes, and you can guess which engine it runs on. But basically, if you read this paper from 2016, it's all about computer graphics. It's all about how we modeled the eyelashes and how we modeled the rotation of the, what's it called, of the apple of the eye, and how we did the optical effects in the retina and everything like this. And this is the whole paper. And then the machine learning part is, okay, now let's take a real world image and let's find the nearest neighbor in our synthetic database and do gaze estimation like this. And it worked better than state-of-the-art. Okay, so this was 2016. Basically, the takeaway point is that by now we have a huge data set of synthetic eyes. We, of course, with labeled gaze directions, we know where the synthetic eyes are looking. And this is where our refinement comes in, right? So this was a very famous paper from Apple in 2017. And in this paper, they took the synthetic images from the previous one, from this database, and they passed it through some sort of an architecture. On the next slide, I will explain what it was. And they changed it into an image of an eye which looked in the same direction, so the label was preserved, the target variable was preserved, but the eye looked more realistic, right? And they showed, so, I mean, obviously you can do things like this with any kind of data set, and it might succeed more or less, but the ultimate goal is you want to improve gaze estimation for real images, right? So they succeeded in this. They actually showed that after training a gaze estimation model on their refined data set, you actually get better gaze estimation than anything people had before. And that was the big breakthrough. So how did it work? For those of you who know GANs, this will be a very simple picture. For those of you who don't, maybe not so easy. But let me just very quickly walk you through this. So you have, because we will see quite a few of these pictures in the future. So you have synthetic images, the source domain images, and then you have the real eyes. And in most of the situations that we have here, including this one, you have synthetic data which is labeled, and you have obviously real data to where the domain where you want to transfer to, but the target domain is not labeled, right? So here you have, you can have a lot of pictures of eyes, but you don't know where they're looking at. So what you do is you take the synthetic data from here, and you put it through a well, it's basically a neural network, which is called a refiner, and in a GAN it would be called a generator. So you put it through the refiner, and the refiner tries to make this image more realistic. So how do we know that it has become more realistic? We know it because we have a separate network called the discriminator that tries to distinguish these modified, refined synthetic images from real images from the target domain, from real images of eyes. And obviously, we want the discriminator to work as poorly as possible, right? So at the end, even a perfectly trained discriminator should not be able to distinguish between our refined synthetic eyes and the real eyes, right? And by distinguish, I mean just binary classification. Is this synthetic or is it real? But that's not the end of the story, right? Because there is one important thing here which distinguishes it from just a classical standard 2014 GAN. And the thing is that you also need to preserve the target variable, right? So if there was no, if this part of the architecture was not here, then the refiner might just learn to output a few real images, right? So it might just not care about the input at all. It might just output, just memorize 1,000 real eyes, output a random sample from 1,000 real eyes, and that's it. It's perfect. The discriminator cannot do anything about it. So we want this refinement procedure to preserve the gaze, right? And how you achieve this? Well, obviously with a separate loss function for the gaze. So you have this, which in Apple's paper is called Psi, it doesn't matter, but you have this function. This is the gaze estimation function. And it has been trained on the synthetic data set. So, and by the way, I didn't mention this, but the rule of thumb is anything you train on a synthetic data set works extremely well on the synthetic data. Right? It's like 99.5% correct, and it predicts gaze perfectly, but as soon as you start to run it on real images, it fails completely. So here you have Psi, which is trained in the synthetic data set, and it works great. And what you actually want is you want your refined image to be at the same time realistic, so it cannot be distinguished from a real image, but also susceptible to the same gaze estimation function. So it should still be, the model trained on the synthetic dataset should still work. And yeah, this sounds very logical, and the loss functions are here. I have a lot of formulas on the slides, but I suppose I will not go into the actual formulas, but I do want to go through these kind of pictures. So this is Apple's refinement, okay? And that was not the end of the story, of course. Later, there was this gaze GAN. How many of you have heard of Psychogains? Psychogains. Okay. So a Psychogan is an architecture that can map images from one domain to another without any explicit correspondence between the images. So for example, you can do like style transfer, for example. Like the basic application of Psychogan was style transfer. Style transfer, like from, I don't know, photos of landscapes to Monet paintings, right? And you can do this style transfer from a data set of landscapes and a data set of Monet paintings without any explicit correspondence, because of course you cannot have Monet draw you a painting of this specific photograph. And how it achieved this, it has generators from one domain to the other and back, and the main loss functions are cycle consistency losses that tell you that when you go from landscapes to Monet paintings and then you go back to landscapes, you should get the same thing, right? So when you go from one domain, from the source domain to the target domain, you have a discriminator there that distinguishes your modified images from the real target domain images, but then you have to be able to go back and get what you started with. And this cycle consistency is a key element in many of these kind of style transfer architectures. So, of course, you can apply this to synthetic to real domain transfer. And this is here, again, the source domain is a synthetic data. The target domain is real data. And you have now two refiners. One maps synthetic to real. The other maps G maps synthetic to real, and F maps real to synthetic. And basically, here you have G F of G of X, and you want F of G of X to be equal to X, right? And here you have G of F of X from the real data set, and also you have to have this cycle, the idempotency in the cycle. So G of F of X equals to X. And you also have the discriminators. One discriminator in the real domain, so the refined synthetic image should be indistinguishable from a real image. And you have a discriminator in the synthetic domain. The refined real image should look like a synthetic image. And then you have, of course, the loss for the gaze, for the target variable. So basically, it's also a very standard architecture, but now it's the Psychogains standard architecture with a gaze estimation loss added on top, right? And it works even better. So this concludes the story of gaze estimation. Why is this so easy? Well, not easy, but why is this a problem which is, I mean, which was the first where synthetic to real domain transfer actually worked? Well, in my opinion, that's because the images are simple. Right, so if even for a real photograph, and I do have a real photograph here, even for a real photograph like this, if you cut out the eye, it's a very small picture, right? And the data set for gaze estimation that we are talking about contains images. I forgot the actual, to put here the actual dimensions, but it's like less than 100 by 100 pixels, right? And so the main problem with GANs is scaling them up. And if you have ever worked with GANs, you know that it's pretty easy by now to do anything you want on 100 by 100 images, but if you want, as soon as you want to scale them up to, I don't know, at least 1 megapixel photos, there are problems, right? And so this is the problem, which is on one hand very practical and very important, and people would pay money to solve it. But on the other hand, I won't say it's simple. It's not simple, but the data is relatively low dimensional, right? The images are relatively small, and you can expect this sort of thing to work out of the box and to actually give you more realistic eyes from synthetic eyes. So when people try to apply this to other domains, when people try to do things like this in synthetic to real refinement in more general situations, for example, this here is an early work on refinement, which also learns a GAN, and this GAN now tries to operate on, you know, like generic images of household objects with depth estimation as the target problem. So now, as you can see, the results are not so stellar, and although it was still a good effort, it did not become mainstream in 2016. Okay, well, I don't have too much time, so probably I will not explain each and every architecture, but basically, by now, we are starting to, we are getting better in this, right? So this is a more recent architecture, T-squared net for synthetic to real refinement. If you look at this, it's pretty similar to the basic Apple refiner. It's a bit different in the loss functions. It has some loss functions on the features, in the discriminator on the features. It's an important idea, but still, if you look at the images, they actually become more realistic, and you actually can see that the refinement is getting better. Oh, sorry, can you please cancel this? probably. Yeah, thank you. And this is one of the latest works on this. It's from this summer. It's about synthetic to real refinement in automatic vending machines. So again, this is the kind of a computer vision problem where you will not have an ImageNet ready for you, right? This is a computer vision problem where, yes, the problem is just to do object detection and count the objects in the vending machine, but you have like a fisheye camera. The images are very specific. The images are very different from images in ImageNet. And the objects that you have to recognize are also very different from objects in ImageNet. Well, they're not very different, but they are more detailed, right? So it's not enough to say that it's a cup. You want to know a cup of what. And here, again, it's a very straightforward paper. You have the synthetic vending machine. You put synthetic images in the synthetic vending machine. You have a synthetic fisheye camera. You take your synthetic images with your synthetic fisheye camera, and then you do the refinement. So you move from a synthetic image, like here on the left, I'm not sure if you can see the details, to the refined image on the right, and it looks much more realistic, and they actually show that the resulting object detection model works better, okay? And the architecture is, again, based on Psychogains. It's a bit more complicated, won't go into details, but basically it's a Psychogain with a few more losses added to make object detection easier. So that was about synthetic to real refinement. Sometimes you can apply, obviously you can apply the same thing in the opposite direction, right? You can take real data and you can try to make it more like synthetic. Question is, why would you want to do anything like that, right? So there is a direct application, which I will probably skip over. A direct application is, as I mentioned, all kinds of models work perfectly in the synthetic domain, right? So instead of getting your synthetic data set, making it more realistic, training the model, and hoping that it will work on real images, you can try to take real images, make them more like synthetic, and hope that your model, which has been perfectly trained on the synthetic data, will work better on real images transferred with this process, okay? This is just like a mirror image of what we have been doing. And the methods are very similar, so I will not go into details of that. But there is a separate application, however, and the separate application is sometimes, for some problems, you do have a data set, and you might have huge data sets. For example, face recognition. For face recognition, there are huge data sets. You can download them. But if you want to do face recognition which is robust to some kind of transformations in the data, which is robust to pictures taken in different conditions, then you begin to run into problems. So facial recognition from a frontal image is basically solved. But if you do face recognition in the wild, as it is called, so for example, you want to recognize rotated faces, then if you look through all of these huge data sets, they all have mostly frontal images. They have very few images of people with their heads rotated at different angles. So when you train a model, it will work fine if you test it on the real frontal image, but it will make much more errors when you test it somewhere around here. So if you want a model which is robust to this kind of transformation, for example, to rotation, let's stick with rotation, you want your data set to look more like this, right? You want your data set to be more, you want to fill in the gaps in the data distribution over here. So this is another problem, this data set bias problem, where synthetic data can help. For example, this dual agent GANs, again, I won't go through through the whole architecture, but basically what you do here is you take a real image like here, and then you do a pipeline which is designed to feed this image onto a 3D model of a face. This is also, of course, a still open problem, but it's being solved increasingly well. So you put your image on the 3D model of a face, you feed the 3D model of a face to the image, and then you rotate the 3D model, and you get something like this, like shown here. And then you refine it with a GAN-like architecture, exactly like we discussed. So you refine the rotated image to make it better, right? And that is how you can take a frontal image and create rotated images of the face, and then fill in the gaps in the data, and everything works, okay? I will skip over this. And the second direction is, sorry, I'm running a bit over, please stop me if you need. So the second direction is changing the model so that the synthetic data, so that the model can train on synthetic data and work on real data without any explicit transformation of the data itself. So the data sets, you leave the data sets as they are, but you do something with the model or the training process. And here, the easiest ideas are basically to share the features share the weights and feature extractors on lower layers of your networks, or to try to learn explicit mappings between features. So for example, you try to extract the features from real images, extract the features from synthetic images, and then learn a mapping that transforms the synthetic features to real features. And then, the other way around, sorry. The other way around, then when you have a real image, you extract the features, you map it to the synthetic, and then on the synthetic you have a model that works fine, right? So I will not spend too much time on that. The main idea in this domain adaptation, in domain adaptation on the model level, the main idea was formulated by Ganin and Lempitsky back in 2014 and has been extended by many people in many different directions. And the main idea is, again, a sort of adversarial training. So you want to extract the features from an image in such a way so you don't have to have explicit different extractors and then a mapping. You just want to extract the features from an image in such a way that then in the feature space it will be indistinguishable whether the features, what kind of domain the features have been extracted from, right? So in the feature space, the domain classifier, this is what they call a discriminator here in this field. The domain classifier should fail, and this is okay. And this is what Ganin and Lempitsky did in 2014, and this is what we are starting to do for synthetic data transfer. So again, okay, I'm running out of time, but basically, you can apply this kind of things to synthetic to real transfer. And one last point, 1 minute, one last point. Again, a very interesting idea that is just starting to emerge, and I think it has great potential for the future. One interesting idea is to try to change the synthetic data generation itself to make it better for the model operating on real data afterwards. So usually what you have is a synthetic data generator that produces the synthetic images, then you train on the synthetic images, and then you try to apply it to real images. So the idea is to close the feedback loop like here. The idea is to take your model, to take the results of your model on a real data set and use this to inform the generator what kind of synthetic data it has to generate. So to be able to work like this, you need to have a parameterized generator, obviously. So you need to have some kind of numerical parameters that you can tweak, that you can change in the generator, and that you can adapt so that the model can work better on the real domain. But people are starting to do this. There is this Metasim framework, which is very interesting. It tries to generate synthetic outdoor environments in such a way that they are similar to real images on the level of probabilistic scene grammars. We'll not go into details. But anyway, this is, I think, one of the most exciting developments of the last couple of years, and I think it will extend further. So thank you. I'm sorry I've run over time, and this is the resume of my talk, and I am open for questions now. Thank you.
Many thanks for Sergey. And we have a few questions for you.
Great. Where will they appear here? Okay. Okay. That's not a question.
One second.
How can we make feature engineering synthetic data? How are reasonable assumptions about it? So I'm not sure what they mean by feature engineering, but I think this ties into my last slide. So so obviously you control the synthetic data generation process, and you can try to tweak the process. Either, well, obviously you will try to tweak it to make the synthetic data more realistic. That's a given. But sometimes you can also tweak it not according to your reasonable assumptions, but according to hard data about how your model is performing on a real data set. And this is, I think, the main answer to this question. So you take the result, and then the result of your model, you learn, you update your assumptions about the nature of the synthetic data that you want to generate. Next.
Thank you. One more.
Good question. Yes and no. So it's about the same. So the domain transfer problem is hard in both directions. But usually it's a bit easier to make the refinement from real to synthetic, of course. So synthetic data is simpler, and it's easier to, gloss over the irregularities of the real world than to actually generate them. So the refinement is usually a bit easier from real to synthetic, but if you just train on a real data set and then try to go to synthetic, might work, might not, as usual. Next. That is also a very big question. So the general answer is not directly, because I think it's kind of self-evident. So if you have a GAN that generates synthetic data, and you can train your model on this synthetic data, and it can work on real data, why do you need the model? Your GAN is already understanding this data. It has the discriminator, which is an even more powerful network that is able to extract the features that you need. So usually it doesn't work like you just train a GAN and then let it generate a data set for you. But in many domains, especially in domains like medical imaging, where there is just little data at all, period, you can try to train a GAN to generate, to do conditional generation of synthetic data for you. So for example, if you have an MRI of a brain tumor, and you have like 10 MRIs with tumors, and then you have maybe 1,000 MRIs without tumors. So what you can try is you can try to ask a GAN to take a real brain without any tumor, and then label the area where you want the tumor to appear, and ask the GAN to generate conditionally on all of this an MRI of a brain with the tumor in this location. Okay, something like this. And then you can actually use it to inform your models that are trying to detect the tumors. So the answer is it's possible, but conditionally and in some restricted domains, not in general. Next.
And last one.
Is there a collaboration of synthetic data and Bayesian learning? Good question. Not that I'm aware of. But of course, if you know anything about it, please contact me. I would be very happy to learn.
That's all?
That's all.
One more.
Thank you.
Applause for Sergey.